We are going to start this topic, stability of control systems. This is a very important topic because stability is a concern when you design a control system, that whether the system is going to be stable or not, or whether if the system is initially stable and initially unstable and you want to stabilize it using your controller, right? But the thing is that what is stability, right? We should first define stability. So stability of a system is usually defined with regards to the equilibrium point of a system. Right? For example, the system itself may be stable or unstable at different equilibrium points. So at one equilibrium point, the system might be stable, and at the same time at the other equilibrium point, the system might be unstable. For example, and through this we'll also try to understand the definition of stability. Right? For example, if you look at this pendulum, right? Pardon my drawing, but this is a pendulum, right? And mathematically, it has two equilibrium points, right? One of the equilibrium point is this, as shown here, where the bob is downwards, and the other equilibrium point is for theta equal to 180 when it goes upwards. This is another mathematical equilibrium point, right? Now, if I disturbed my system from this equilibrium point, a small disturbance, mind you, the disturbance has to be small, right? I'm not talking about large disturbances, but small disturbance from this equilibrium point. So system will, or this pendulum will, in due course of time, return to this position, this equilibrium point. And if that happens, that will surely happen with the system, then that equilibrium point of the system is a stable equilibrium point. On the other hand, for the same system, this equilibrium point, if you give it a little bit of disturbance from its equilibrium position, the system will move away from this equilibrium point and start oscillating about this equilibrium point. Right? The oscillations may be large, but they will eventually die down at this equilibrium point. So this equilibrium, the upward position of the pendulum, was a unstable equilibrium point. Right? So that is the definition of stability as well. That if you want to define stability, it is that when a system, when disturbed from its equilibrium position, returns back to its equilibrium position in due course of time, in finite amount of time, then that equilibrium point is a stable equilibrium point. And if it does not, if it keeps on growing or moves away from that equilibrium point, then that equilibrium point is a unstable equilibrium. Right? So the definition in our terminology is that we usually discuss about the free response only, the natural response of the system. Why do we do that? Because stability is a property of the system, right? It does not depend upon the input you are giving to the system. Stability is a property of the system, so it only depends upon the free or natural response of the system, right? And so if the free natural response goes to zero with time going to infinity, that's a stable system, right? And if the natural response grows without bound, it keeps on increasing, then as time goes to infinity, then it's an unstable system. And if it neither grows nor decays, then it's a marginally stable system. So these are the three cases. Generally, it may not be possible to separate the natural response and the forced response of a system. So in that cases, we define the BIGO stability, that is bounded input, bounded output. So if the input to the system is bounded and the output of the system is also bounded, then we may also call the system to be stable, right? This is only for the case where we cannot separate the natural and forced response, and that is when you are practically dealing with systems. But in our cases, we would actually be restricting to this definition of the stability. Right. Now I've shown some figures here. I think this is the stable case because this is actually the system, our favorite system from vibrations course, where C is positive, and if C is positive, then we know that this will die out, right? Depending upon whether it's an overdamped system, we are not going to go into that, but it will die out and reach to its equilibrium position. Similarly, if C is negative, you can see that it will keep on rising and its system is unstable. Marginally stable is a undamped system where you have seen it, the response is just sine omega t, right? Now this is the figure which is usually used for defining these three forms of stability. This is an unstable equilibrium point. This is a stable equilibrium point. Why is this unstable? Because if I give it some initial disturbance from this equilibrium point, it will move to some other equilibrium point, right? This is a stable system. If I give it some small disturbance, then it will come back to its position, this position. Again, the small disturbance is important because I may give large disturbance and it might move to this equilibrium point. Right? So it's the small disturbances that we're talking about here. Then this is a marginally stable because if you give it small disturbance, then it will remain here only. Right? It won't neither go here, neither come here. So it's a marginally stable system. This is just for our understanding. Then we want to relate the stability to system poles, right? So because we have been doing everything with regards to poles now till now, so we want to relate the stability of the system with poles, right? So how can we do that? Well, since we have been talking about the transient response or the natural response of the system, so we know that if the real part of the poles is negative, right, then the response dies down, right? And real part negative means the pole lies on the left half of the S-plane, the shaded region in this S-plane. If the pole lies in this region, then the response will die down, right? So if poles are on the left half of the S-plane, then natural response will decay with time, right? We know this, we have done this, right? If it comes on this side, then what will happen? E to the power positive t will come outside. Right? If positive t come outside, means it keeps on growing. So if the system poles are on the left hand side of the S-plane, I'm again repeating, then the system will be stable, right? Again, it has been written here that a real power of the pole is less than 0 for stable system. So all the poles should be on the left hand side. If there are multiple poles, they should be on the left hand side for the system to be stable. Even if one of the poles is on the right hand side, then the system becomes unstable, right? I think this is fine. I think this is again repetition of the same thing. Stable system, all closed loop poles, now I'm using the terminology closed loop poles, should be on the left half of the S-plane. Unstable system, any one of the closed loop is on the right half of the S-plane. Right. Now what is the difficulty in this, right? The difficulty is that it's not always possible to find the pole locations. For example, you know the poles of this system, but this is an open loop system, right? This is just a system. We would like to know that with the control, feedback control, whether the system would be stable or not. But we do not know the closed loop poles, because if you do the math here, it will be difficult to find the closed loop system poles, right? And by this time, I think you know what is closed loop transfer function, what is open loop transfer function. So you can find the closed loop transfer function using the formula gs upon 1 plus gshs, right? So if you try to do this, it will be difficult for you to find the whether the system is stable or not, or what are its pole locations, right? Because pole locations will determine its stability, right? But again, to our rescue comes the mathematicians who have always helped us. So this time it's a guy called Ruth Hurwitz, and the criteria is called Ruth Hurwitz criteria. It's a method of finding the stability information without solving for the system poles. So we do not solve for system poles. It is not a solution technique, but this criteria actually helps you in finding the stability of the system. And how does this do that? You can find how many poles are there in the left half plane, in the right half plane, or on the imaginary axis, right? How many poles are there? It does not say where actually are the poles, but only how many are there on the left, how many are on the right, and how many are on the imaginary axis. That is all this Routh-Hurwitz criteria tells us, right? It will not be solving for the system poles. Okay, but you might be wondering that, well, we have MATLAB and we can find the system poles even if it is 100th order system. So it is more useful in designing the system rather than finding the answers. Because when you're designing, when you're analyzing a system and you want to design a controller, right? You don't want to find the poles, but you want to find the value of your controller gains, K, for which the system would become stable. So you cannot use MATLAB for that, right? You can use, but you will have to go for symbolic toolbox and all that. So you will find a relation for K with respect to system poles and then solve for K for which the system pole becomes negative or positive, right? That may not be possible if you just try to do something numerically, because doing numerically you cannot have an unknown K in the system. You'll have to have proper analysis, right? So that is where this comes in handy, that you have a proper method of finding, analytical method of finding the stability. Right? So what are the steps involved in doing this? First step is you have to create a table which is called as Routh's table, and then second is you interpret the table. That and then these two steps will be done, right? That you interpret the table whether the how many poles are there on the left half plane and how many poles are there on the right, right? So